Hello everyone, and thanks for tuning in from home. I'm Henry Foster. I go by Toadstorm on the internet, and I'm the developer of MOPs, the motion graphics toolkit for Houdini. Those of you who are familiar with Houdini probably know that Houdini has a reputation of being great at making hard things easy and easy things hard. It's an incredible piece of software that's capable of doing just about anything you can think of, but it expects you to know exactly what you're doing in return. For skilled technical artists, this isn't as big a hurdle as it is for those of us who went to art school and forgot all our math classes. However, even for those smart guys in the room, there's still time spent typing out all the necessary code, remembering the order of operations for matrix multiplication, remembering to convert from degrees to radians, or maybe it's degrees after all if you're an H script and not Vex. This is time that you could otherwise be spending making art. MOPs aims to abstract away some of that boilerplate setup work without sacrificing Houdini's power and flexibility. You can think of it a little like an extra UX layer on top of Houdini. Everything MOPs does is native Houdini, just with a few words of encouragement and a shoulder to cry on. The initial design goal of MOPs was to enable something I like to call gestural animation. I don't know if there's already an established label for that, but what I mean by gestural animation is the ability to make lots of complex motion with just one or two keyframes. You might be animating hundreds or thousands of objects, and each one might be displaying very different behavior, but all you're doing is sweeping your hand across and saying, go that way. It's a really powerful and gratifying way of animating that's used in Cinema 4D's MoGraph and Maya's Mash. Complex behavior with simple controls. MOPs take this a step further thanks to Houdini's open nature. The core operations that MOPs is doing, mostly related to transforming objects, are exposed to you as low-level tool nodes that can be utilized by anyone as building blocks for creating more complex behaviors and tools. These nodes are all native Houdini and Vex, so they can be used anywhere in your networks with few exceptions. They're just setting attributes like anything else in a SOP context. MOPs can work both with packed primitives, or instances, whatever you want to call them, or with points, setting primitive intrinsics or template point attributes interchangeably. If you prefer the traditional Houdini way of copying the points, you can still use almost all of the MOPs modifiers to adjust the attributes of those points and then copy like you normally would. If you're new to instancing in Houdini, let's go over the basics really fast. To copy an object to a lot of points, you use the copy SOP. A copy of your input object gets placed at every point in the second input. If you want to vary the rotation or scale of these copies, you use what are called template point attributes that the copy SOP and instance object look for. Position and scale are pretty straightforward, but rotations need to be defined as a set of three vectors. These are typically the normal vector, or n in Houdini, the up vector, and a third binormal or bitangent vector that you don't really need to worry about because you can automatically derive it from the first two. These three vectors tell the copy SOP which way is forward, which way is up, and which way is sideways. The three vectors together create what's called a transform matrix that define the object's rotation and scale in space. This matrix is stored in each instance, or packed primitive, as an intrinsic attribute which is secretly lurking in the geometry spreadsheet. If each of your template points has different n and up attributes, this will make each copy face towards the n vector with its vertical axis pointing towards the up vector. This system allows you to be very precise in how your copies are transformed, but it's not exactly intuitive to figure out which way you might want n and up to be pointing when you're used to thinking about rotations as 90 degrees left or 15 degrees up, and it gets even worse when you want to animate these rotations and are suddenly exposed to words like quaternion and slurp, and now you really need a drink. It's easier to just show what this framework is doing rather than talk about it, so let's jump into an example. For anyone who's following along at home, or anyone digging into the examples later, I'm using MOPs Experimental version 1.1.1. Here's an imaginary situation where an art director is giving you very specifically vague instructions on how he wants to construct a grid of pig heads. So here's the initial ask. I need a grid of pig heads. Can you make them look in random directions, but only side to side, and not too much? Okay, let's make our pig heads. I'm going to start with a grid and a pig head. Copy the points. And now their default orientation is going to be wrong, so let's set up some point attributes. We're going to set n to be positive z and up to be positive y. And let's set p-scale to be a little bit smaller because the default is a little too large for this grid. And there's our initial pig heads. So now what we want to do is get them to look left or right randomly, let's say up to 45 degrees. So to do that rotation, what we need to think of this as is a rotation around the up axis. So around positive y, left or right, 45 degrees. There's a few different ways to approach this, but one of the most straightforward ways is to create a transform matrix because they can be easily rotated in Vex. So let's make a matrix, and now we're going to rotate this matrix randomly 45 degrees left or to the right. So we need to create a random angle. We're going to fit that between -45 and 45. Next, we have to actually rotate the matrix. We need to convert this angle to radians because matrices don't deal with degrees. And we're going to rotate it around the up axis we defined earlier. Now that we have this, we can just multiply our initial normal vector by this matrix. And now we should have a rotated normal vector. Okay, our hypothetical art director is back with some notes. He says, can you scale them randomly? Well, this should be no big deal, right? We can just use the attribute randomized SOP to handle the p-scale. Set the attribute to p-scale. Minimum, let's say, is 0.2, maximum is 0.8, and we're good to go. The reason we couldn't use attribute randomized to handle the orientation is because we were rotating a specific number of degrees around a specific axis. Attribute randomized can do a lot of things about randomizing orientations, but it's not very good at accepting very specific instructions like that. That's why we had to resort to vex. But for p-scale, this is all we had to do, so we're done, right? Of course not. Your art director comes back and says, wait, I want the ones on the outside to be really small. Okay, I'm not sure exactly what he means by the outside, but just to be safe, I'm going to make a shape that I can transfer a color attribute from and use that as a mask to multiply against p-scale. So I'm going to make a sphere. I'm going to give the sphere a color. I'm going to give my grid points a default color. And then I'm going to attribute transfer from one to the other. Transfer the color attribute, CD. We'll change our conditions to get a nice looking mask. Something like that. Next, we're going to multiply p-scale by this value. And then afterwards, so our copies don't inherit that color attribute, we've got to delete it. Great, okay, outsides are smaller than the inside. We're good, right? Can you make the ones in the middle look up towards the camera? Well, this is going to be fun. The way we're going to approach this is by making a transform matrix that aims at the target, which happens to be the camera in this case, and then we're going to blend it with the existing transform matrix to get the final result. So first I'm going to make a point in space that's going to represent the camera. This is going to be my target. Next I'm going to drop down a point wrangle and wire the sphere into the second input. So first thing we need to do is define our target matrix. And now we need to make another transform matrix that represents our current transformation. Next, we're going to blend them together using the slurp function. In Houdini 18, you can directly slurp transform matrices, but if you're in an earlier version, you'd actually have to convert these matrices into quaternions first, slurp them, and then probably convert back to matrices again. Once we have the matrix defined, now we're going to set n and up according to this. Again, we could bind this to orient, but I'm just trying to stay consistent with n and up for now. Okay, now the heads are looking up towards that target. You can see if I move this camera target, the heads are looking at it, and the closer they are to the center point, the more they're looking. Last thing, I promise. Can you make them just bob around a bit? You should never believe an art director when they tell you there's only one more note. Anyways, the easiest way to get around this is to use a point VOP for the noise functions. Inside, we're going to lay down some curl noise. And then to make the curl noise easily evolve over time, we can convert it to a 4-dimensional noise. The first 3 components are going to be P, and then I'm going to use time as the 4th component. In case I want to change how quickly this evolves, though, I'm going to add in an extra parameter here to multiply against the input time. Next, I connect that to the position lookup of the curl noise, and then promote the other parameters. Then I'm just going to add the output of that to P. Okay, those pig heads are definitely bobbing. Ooh, and now can you make them all form into one big pig head at the end? Well, you had to know something like that was coming. So let's start by making a pig head. That's going to be our goal, and we're going to scatter exactly 100 points on it, which is the same number of points that we have in the original. And we got to, again, set some basic template point attributes for it. So N is Z forward, and Y is Z up. And we'll set a base P scale for it. And now we're going to have to blend the point position, the P scale, and the orientation of these destination points in with the originals. So another point wrinkle. So let's fetch all those attributes. Now I'm going to make a transform matrix out of the goal attributes that I've just defined. And now I have to make a transform matrix out of my current N and up. Now I'm going to make some kind of attribute to blend the two together. So that handles blending the orientations together. Now I've got to do the same thing for P and P scale. Now I can animate the slider channel and the pig heads will move towards their goal. If that whole section seemed a little tedious to you, it was supposed to. I don't like typing out all this code any more than you like watching me do it or listening to me do it because I'm a big nerd with a loud mechanical keyboard. And you can imagine it would take a lot longer if you were at all rusty with the math or with Vex. So let's try doing this effect again, this time using a few MOPs nodes. All right, let's start fresh with another pig head. And I'm going to pipe this into a MOPs instancer. This is kind of like a copy saw, but with a lot of extra built-in controls to help make it faster. I'm going to set the distribution to grid, and I'm going to set the size to be 10 by 10 to match the other grid that we used, and then set the step to 1, so I've got exactly the same number of pig heads. Then I'm going to set the global transform to bring the scale down to about where it was in the other one. Okay, and we've got our pig heads. So next we need to make them look around randomly. MOPs randomize has an option to randomize orientation, and you can pick which axes you want to randomize on. So I'm just going to randomize -45 and +45 around Y. So that's done. Next, I want to shrink the ones that are on the outside. So to pick the region of things that I want to shrink, I'm going to use a MOPs shape falloff. The shape falloff is more or less setting that weight or blend attribute that I was setting earlier. It's just doing it with a better interface. I'm going to enable preview falloff so I can actually see what this thing looks like. I'm going to set my shape to spherical, and then I'm going to scale this up a bit. I'll disable this shader so it gets a clearer view. Next, I'm going to use the MOPs transform modifier. This actually sets transforms on packed primitives, but it does it in their own local space. It'll also work on points and just update the template point attributes accordingly. So if I scale down, I actually want the opposite of this effect. So I'm going to go back to the shape falloff and just go to remap, and then fit my output range from 1 to 0 instead of 0 to 1. Next, I want to aim these guys towards the camera. So I'm going to grab that same sphere that I made before from the last example, and then use that as the guide for MOPs aim. I'm going to set the aim method to target object, and then I'm just going to disable that fall off preview really quick so I can see this a little bit more clearly. Now it looks like I've actually got this backwards because the fall off needs to be higher in the middle this time around so that the objects in the middle are actually aiming at the target. So I'll use a remap fall off node to again just invert the fall off that I had going in. Now all these guys are looking at the target. So next I got to get these guys to bob around a little bit. For that I can use the MOPs noise modifier, which has all kinds of built-in noise patterns that can apply to position or orientation or scale. I'm just going to tweak these settings a bit. I'll disable fall off, change the amplitude a little bit. Can automatically make this time varying noise and then change the time scale down just like I did in the other example, but now it's all built in. And the last thing I need to do is blend these guys in with that final pig head shape. So I'm just going to copy the template points from the previous example, bring them over here. And then I'm going to use MOPs apply attributes, which is one of those low-level API nodes. What this will do is take the template point attributes from this second input and apply them to the first based on some simple rules. I'm going to create a plain falloff, which just sets a flat falloff value for everything on this side. And I'm going to tell my fall off thing to set the rotations and then replace the scales. Now you can see as I animate this slider, everything just moves right into place. You can see how, even if you have the technical know-how to address the endless stream of nodes, all of these little things start to add up very quickly, and there's a lot of time spent fussing over the implementation rather than getting the shot done so you can go play Animal Crossing. MOPs can reduce a lot of that clutter and let you think a little more conceptually rather than technically. Okay, now we can get to the fun part. Unsurprisingly, MOPs has plenty of applications in motion graphics. Let's go over a few typical motion graphics examples to see how it all works together. Animating type is a very common thing in the motion graphics world. You're rarely animating words as a whole, though. Usually you need to be animating letter forms separately. In this example, we need to do a quick bouncy sort of reveal. This would be pretty annoying if we had to group each letter and then keyframe transform stops individually, setting the pivot point every single time, so let's not do that. Okay, so here I have a pretty basic text setup. I have a font sop, I'm extruding it, and then I'm setting vertex normals. The only interesting thing here is that on the font sop, I've enabled add text attributes. This means that on the primitives, I'm going to have attributes that tell me which primitive belongs to which letter form. I'm going to need that later. So first what I'm going to do is I'm going to assemble these into packed primitives. And there's all kinds of built-in tools that you can use to do this, but I've built one called MOPs Convert, which makes it a little bit faster and easier. All I have to do is tell this thing which attribute that I want to use to define which letter form, and I have that already. Now if I middle mouse button here, I've got 10 packed fragments, one for each letter. If you check the attribute spreadsheet, each of these packed fragments also already has a name attribute and an ID attribute built in. And you can change the prefix or the start number that the ID starts with, just in case you're trying to merge multiple streams together. These attributes are used by MOPs in order to know what attributes to assign to what piece, but they're also used by things like the packed RBD solver in order to differentiate pieces in the simulation. Next, if we enable point display, we can see that the pivots of each of these objects is in the centroid. And that's not really what we want. We want these things to animate up from the bottom. Normally changing the pivot points of packed primitives is pretty tricky. You have to worry about what kind of orientation and space that they're in, and you have to actually move the primitives, the P attribute, in the opposite direction of the pivot adjustment that you're making, and that includes the orientation of the object, so it can get really confusing. Instead, I have MOPs Align, which will do all that for you. I can just set the mode from center pivot to align to B-box, and the default is -Y, which means everything will be aligned to the baseline. Next, I'm going to animate a fall off that sweeps across. I'm going to use a shape fall off. I'm going to rotate it into position, and then scale it up a bit. And now I'm going to keyframe it animating across these letters. If I enable preview fall off on this, you're going to see that all of the letters change color at the same time, and that's because these are packed fragments. And this is an issue with the viewport shader. It just doesn't know how to differentiate packed fragments because of the way that they're optimized. So if you go to fall off preview, you can enable display as sprites, and this will enable each of these packed primitives as a sprite so that I can see the color changes individually. Next, I'm going to apply the transform. So I'm just going to scale down on the y-axis down to 0. Now this is going backwards again, so I'm going to just remap this fall off real quick. Now these things are popping up, but I want that spring motion, that kind of extra bounce that gives it a little bit more character. And for that, there's MOPs Spring Modifier. The spring modifier is a very simple solver that adds physical forces to different attributes. You can add spring forces to position, rotation, scale, fall off, or a few other things. Because this is a simulation, the first thing I'm going to do is just reset it, just to make sure everything's clean. Next, I'm going to adjust the mass and the spring constant. This just sets the various properties of the springiness, how much follow through it has. And I'm going to set this up to only apply to scale. Now that same animation has a little bit more bounce to it. Finally, the last thing I want to do is just make it so that I can't see these primitives before they pop up. And remember, these are just regular Houdini packed primitives. There's nothing special about MOPs primitives, so anything you can do with regular packed primitives you can do here. So I'm just going to set up a blast. And then I'm going to erase any primitives where the fall off value is greater than, let's say, 0.95. Since MOPs fall off is a point attribute, I just have to change the group type to points. And now these things only show up when they start animating. Okay, on to the next example. Here's a quick little transition effect that you might commonly find in the motion graphics world. MOPs can affect polygons or clusters of polygons in the same way that it affects packed primitives by using the MOPs explode SOP to break the polygon faces into packed fragments. Let's get started by generating one of these rubber toy test geometries. And then we're going to remesh it so we can get some smaller faces. Let's set this to about 1/10 of what the default is. Okay, and then let's run it through a divide SOP. This will give us slightly more interesting shapes. I'm going to just enable compute dual. And now we get this kind of interesting soccer ball pattern almost. So now we're going to run this through MOPs explode. And by default, it's going to take every single primitive and break it into a separate face. We can check that out by going to define pieces and then enabling visualize pieces, and this will show us that each of these primitives is becoming its own packed fragment. You have options to also use things like clustering or a special piece attribute, which would be a primitive attribute that you can use to define what gets added to what chunk. For example, if I turn on clustering here, I can have these things automatically use k-means clustering to group pieces by the p attribute or any other attribute you define. I'm going to leave this at the default to just split by primitive number for this example. Next, we want the effect to start at the tail and work its way across the head, so the spread fall off we used earlier is probably a good candidate for that. Now for the spread fall off, I can either use a group mask to define what the starting points are for the spread, or I can use points in space. I prefer using points in space for this because it's a little bit more procedural. Now I'll connect that to the second input of the spread fall off and then set this to be point cloud. I'm going to turn the distance threshold down because by default this is going to spread over a wide area initially and we only want it to spread to a little bit at a time. I'm going to enable preview fall off, and then again, because these are packed fragments, I need to enable display as sprites, and then I'll scale these way down because they're going to be too large by default. So now I can get a clear view of the spread as it happens. I'm going to go to the Animate tab and then drag across, and this looks okay. I might want a little bit more fall off width to soften it a bit. It's a little bit better. And then to make the pattern a little bit more interesting, I can add a bit of noise. Maybe we'll change the frequency a bit here and make it more visible. Increase the amplitude just a hair. That looks okay. Okay, let's disable fall off preview. Now we can do our first transform. You can use the MOPs transform modifier. For this first part, I'm just going to flip these things 360 degrees on local Y. And what this is going to give us is kind of a ripple effect as that animation goes across. So I need to set a couple of keyframes on this. We need to animate until we see the ripple go all the way across. So that's going to be about 1.4. So this is already kind of an interesting transition effect. The width of it might be a little bit broad, and if we want to turn that down, we can adjust our fall off width. That looks a little bit more contained. Now I'm going to go back to the MOP explode and disable the visualize pieces here so I can get a less colorful view of what's going on here. So this is already a kind of neat little ripple effect, but what I want to do is have this thing actually animate on like it's materializing out of nothing. So I can do that with another MOPs transform modifier. I'm just going to have these things scale to 0. And actually it's disintegrating now, which is the opposite of what I want. So let's go back and make another remap fall off node. and switch the output minimum and maximum. So this thing is almost where we want it, but let's make it a little bit more interesting and move these pieces out a bit. The nice thing about MOPs Explode is that it automatically generates a local coordinate frame for each of these packed primitives based on the orientation of the original surface. So that way, if we go back here with the MOPs transform modifier, and we translate these pieces along their local z-axis, that's equivalent to the primitive normal. So that can be really handy when you're trying to actually blast pieces outwards. Normally, if you were to break something like this apart using an assemble SOP or something like that, these pieces would have no idea what their own local orientation is, and a translate along z would just move along world z. But MOPs Explode handles a lot of that for you. Let's delete that and go back. Okay, so 3 might be a bit much here. Let's try 0.3. There we go. So because these things have already been rotated, and we're transforming in local space in the following transform, this means that the pieces are going to have this sort of interesting wavy motion because they're rotating as they transform. We could also probably get a similar effect by adding in some curl noise or some other function in here to kind of mess up the rotation frame of these things as they move, but this works pretty well by itself. Here's another little motion graphics toy. Moving objects along paths in Houdini isn't too bad at the object level using chop constraints, but this gets busy very quickly if you have a lot of objects. You can do it manually at the SOP level, but you'll likely be doing it in Vex using the PrimUV function to manually define the parametric length along the curve that you want to sample your attributes from before applying those attributes to your objects, and that's not even taking into account behaviors like wrapping from the end back to the beginning or maintaining any sort of offset from the curve. MOPs handles all of that pretty easily. Let's start by generating the initial line that we're going to move these squabs along. I'm going to resample it. And then to bend it into that fountain shape, I'm going to use the guide process SOP in bend mode. Let's change the mode from root direction to axis constant, and that just lets me arbitrarily define an axis to bend along and then change the angle to 90. So now I get this nice 90-degree bend. Next, I'm going to offset this curve just a little bit from the center, maybe here, and then use the copy and transform SOP to actually copy these things around the center. Now, let's say I want 16 copies. That seems like a decent number. What I'm going to do in order to procedurally distribute these around the center is just use a quick expression. 360 degrees around the circle divided by the number of copies. This means that no matter how many of these I pick, I'll get an evenly distributed set of curves. Next, let's make the squab we want to copy. And then I'm going to use a MOPs instancer. And these are enormous, so let's make those a little bit smaller. I'm going to go to the global transform and change this to 0.02. And then on the distribution method, I'm going to change the type to from the default grid to curve, and then just grab and drag these copied curves over the template object. So now I have squabs in all of these curves nicely distributed. They're sideways though. So let's go to our orientation settings for the curve. And because reorient curve is enabled, I can just take this and twist the curve by about -90 degrees to get it into the right position. If you need more precise control, you also have the ramp here. Another way in MOPs that you can orient things is by using the MOPs orient curve SOP. If I disable reorient curve here, you can see that these guys have no way of knowing which way they're supposed to be facing, so they're just picking sort of a default orientation. There's also in Houdini 18 something called orientation along curve, which is a SOP that you should check out. It's very powerful. For those of you who are not on 18 yet, I'm just going to stick with the MOPs orient curve SOP. So these controls are more or less the same as what you have on the instancer because it's the same SOP on the inside. It's using an algorithm called parallel transport, which is a great stable way of generating orientation frames, but it's hard to debug these if you can't see them. So another really handy node that exists inside MOPs is MOPs Visualize Frame, which just quickly generates a sort of little gnomon visualizer that points out the up, normal, and side vector of each point. So you can see that the up vector, which is represented by this green line, is facing sideways, and that's why my squabs were all facing sideways initially. So I can go to my curve orientation and then change that same twist control to -90 to get a better result. If I go back to the instancer, I can just use the MOPs orient curve as my template object. And now they're all facing the right way. Next, I'm going to use the MOPs move along spline modifier. I'm going to connect my squabs into the first input and then my curves into the second input. So they're all just sort of dumped onto this one line right now, so I need to change a few settings. Under the Attach tab, this is where I define the starting positions for each of these things at the beginning. Right now, all of these squabs are in the wrong place because they're being told by default to attach to primitive number 0, which is this curve right here. Instead, I'm going to change the curve select mode to use nearest. Now, it looks like they're in the wrong orientation again, and that's because reorient input curve is on by default. If I turn this off, it's going to use the orientation that I defined on the instancer. Now, if I go to the Animate tab, all I have to do is just animate the goal slider, and by default, these guys will slide along the curve, oriented along with it, and they'll wrap from the end to the beginning as they pass to the end of the curve. But this is a little bit boring. They're all in exactly the same place. So I'm going to offset their initial position using a MOPs randomize. I'll take the minimum down to, let's say, 0.1 and the maximum 0.1, just in opposite directions. Now, you'll notice that they're randomized along the curve now, but they're not maintaining their offset from the curve in all three axes, just along the curve. So what I need to do is go to my Attach settings and enable Maintain Offset. And this slider allows you to blend between the original position and the new one. The best part is that this offset translates along the local coordinate frame of the curve. If you want to see what this actually means, you can enable Visualize Offset, and this will draw a visualizer that shows you what's happening to that offset as these objects slide along the curve. If I go back to the Animate tab and change the goal, you can see that that offset is persistent and stays in the local coordinate frame of each curve as it slides across. This will even work if I go to the original orientation and twist the curve. So you can see that the offset is actually updating according to the local space of the curve. You can get some really interesting twisting effects out of this. I'm going to go back and disable that visualizer. Now, another thing I can do is I can modulate this offset based on the position along the curve. So I want these things to be a little bit tighter in at the beginning and then spread out towards the end. So I'm just going to use this ramp and then maybe dial this in a little bit. And now as they animate, they start very close to the curve, but they spread out towards the end. Now, the last thing I want to change here is that it's a little bit distracting when these guys pop on and pop off. And a really cheap way of dealing with that is just having them shrink towards the ends. Now, right now, if I wanted to know what the position was of each of these things along the curve, I'd have to use a primuv function and an xyz dist function in Vex to figure out the closest parametric location to each curve along blah, 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 blah. It's a lot of work. Instead, I can just enable keep goal attributes. And now I have an attribute telling me what the goal is in UV space and the curve number that it's attached to. I can use this to drive a fall-off attribute. If I set my input attribute and change it from the default MOPs falloff to goal, and then enable preview falloff, you can see that the falloff is greatest on the outsides. What I want to happen is for these things to start small, reach their maximum size fairly quickly, and then fade out again at the end. So I'm going to use the remap function to do that. And then I'm going to change my output minimum and maximum again to 1 and 0 to invert that curve. Now if I apply a MOPs transform modifier, I'm going to disable that fall off preview just to get rid of these colors. I can just turn the scale down, and if I go back to the move along spline and animate the goal attribute, you can see that they fade in at the beginning and fade off at the end. It's not bad for a few minutes work. MOPs was originally built with motion graphics in mind, but there's no reason it has to be strictly used for motion graphics. It turns out that animating things happens in visual effects too. Let's take a look at a few different ways you could apply these tools outside of motion graphics. Apply attributes is mainly intended to modify either packed primitives or attributes on template points. However, there's nothing stopping you from using it or many other MOPs nodes on regular old polygon geometry. Here I have a model of our good buddy Paul from Side Effects Labs that I've mangled into something more akin to the Elephant Man. But let's say I only want to make it look like he was stung in the face by a swarm of bees. I can use MOPs Falloff and MOPs Apply attributes as a kind of simple blend shape with weighted deformations, something that you can't currently do with regular blend shapes in Houdini. Okay, first let's bring in our buddy Paul. And we'll subdivide him just so we have a little bit more geometry to work with. Okay, now let's use a mountain sop to mangle him. Now that already looks great. Change the height to something a bit lower, lower the element size so we get a higher frequency of noise. Let's go for Whirly. That already looks lovely. Okay, so let's say this is the look that we're going for. Now, if I were to do this as a regular blend shape, I can blend it from A to B, but blend shapes don't accept any kind of weight channel. So instead, I can use MOPs Apply attributes. Now, the default is just going to completely transform him, but I can use any of the MOPs Falloff nodes to decide what parts actually get affected and what parts don't. I'm going to enable Preview Falloff, go to the Shape Falloff here, and just rotate it into a better position. I think we want this the other way around. And then try to get it positioned and scaled so that it's just affecting his head. There, that's a little bit closer. Now if I go back to Apply Attributes, disable Preview Falloff, I have sort of a real cheap blend shape. It doesn't interpolate all of the other attributes the same way a normal blend shape or a deformation wrangle would, so you're going to have to compute your own normals afterwards. But this is a great way for me to turn Elephant Man Paul into Stung by Bees Paul. Here's another pretty cool effect applied to a mesh instead of points or packed primitives. MOPs Delay can offset any point attributes, including P. This can give you a kind of Slit-Scan or shutter roll effect on moving geometry. Okay, so for this demonstration, the first thing I need to do is grab a person running around. So fortunately, Houdini has some built-in mocap geometry that we can steal for this. I'm going to grab mocap biped 3. I'm going to set his animation type to walks and turns. And then I'm going to grab walk turn 90 left. For shutter roll effects, spinning movement works really well to make things extra wiggly rather than just moving forward. Next, I'm going to hide this and then drop down a new geometry container. I'm going to object merge that character into this network so that I can manipulate him in SOPs. So geoskin here is where the mesh is stored. Now I have him walking and turning. It's really exciting. So let's make it more interesting. First, I'm going to retime this clip because this kind of trippy shutter roll effect tends to work a little bit better when it's in slow motion. So I'm going to change this to fit range and then retime him to about 1 to 100 or so. Now he's a little bit more liquid. Next, I'm going to drop down a MOPs Shape Falloff. Now for this kind of shutter roll effect, I want the top part to be delayed less or more than the bottom part. So I want the axis to be vertical on this. You could set it up to be whatever you want. You might get some really crazy effects, but for a traditional shutter roll, the axis that you're delaying on is usually just either U or V in the camera view. So let's align this. And preview this just to make sure. That looks about right. So before we start using MOPs Delay, because we're just using regular old points here, most MOPs nodes really prefer that you have either an ID attribute or a name attribute in order to tell what points are what. That's because in a lot of situations you can have points appearing or disappearing. An ID attribute is a great way to prevent a changing point count from messing up your simulation. To do that, I can either use an enumerate SOP, set it to points, and then change the attribute to the ID, or I can just drop down a point wrangle and set I at ID equal to the point number. Either one works. Now that I have an ID, I'm going to run MOPs Delay. MOPs delay delays all of your incoming point attributes, including P, based on the falloff attribute multiplied by the maximum delay amount that you've set. So I'm going to set this, leave this at seconds, and then change my maximum delay amount to be about 3 seconds. And that's going to be scaled by the falloff attribute we set earlier. Since this is a simulation, I'm just going to reset it real quick just to make sure everything's clean. And now when I play, you can see that the top of him starts moving sooner than the bottom. With the right kind of motion, this can look just absolutely wild. Here he is wiggling around at full speed. Now, if I go back up here and add some noise to this, things can get really strange. Maybe a little too strange. Move along spline is a pretty easy way of getting points or primitives to move along a curve. This has applications for rigging. One obvious example is a conveyor belt or tank treads. So for this demo, I'm starting with just a box with some normals on it and a polygon curve. I'm going to start by using the end SOP to turn this into a polyline and change close U to unroll with shared points. That means that this curve is still going to be joined, but the points are going to be shared, so we're not going to have a discontinuity in the line. That would make the orientation weird at the ends. Next, I'm going to resample. Change this to subdivision curves, then add a point wrangle. Set the p-scale to about 0.1, and then let's copy to these points. So these are in the wrong orientation. But we can fix that either on the spline, the move along spline modifier, or we can add a MOPs orient along curve. I'm just going to use the spline modifier to do this. First, I'm going to make sure that these are packed, and then I'm going to generate an ID attribute for these using enumerate. Set this to points and set the attribute to ID. And now I can use the spline modifier. So the default is already pretty close. It's almost aligned. There's some nasty orientation on the edges here though, so I'm going to go down to my reorient settings. I think what I'm going to do first is actually resample this again, because part of the problem is I have the right number of samples to just drop these copies on the input curve, but I don't have enough to smooth out the orientation here just yet. So if I enable resampling, change this to subdivision curves, and then lower my length quite a bit, now I'm going to get smoother bends around the edges here. That's perfect. And now all I would need to do is set an expression on the goal. And I already have a pretty good start for doing something like tank treads or a conveyor belt. Let's slow that down a bit. So you can see how this would be really useful for the beginning of a rigging setup for something like this that needed to have treads. And you can imagine how all of the other MOPs modifiers that are built to change the orientation of curves, rotate objects in their local space, and so on could be useful in a rigging context when you're deforming objects in SOPs. Falloff nodes in MOPs are really, really versatile. All they're doing is setting a single point attribute according to some simple rules. Considering how much you can do with point attributes in Houdini in general, you can imagine this makes falloffs applicable almost anywhere in Houdini. In this demo, we'll use falloff nodes to art-direct a destruction sequence, and then use a couple other MOPs nodes to fine-tune the results. Okay, so first things first, we've got to shatter a squab. I'm going to break this into, let's say, 500 pieces. Now I'm going to use the assemble SOP to convert this into packed fragments that are prepped for RBD destruction. Create packed geometry. And you can see I've got, well, approximately 500 pieces. Next, I'm going to add an ID attribute. I could do this with MOPs convert, or I could just do this with an enumerate SOP like I have been. Now that my initial setup is figured out, what I want to do is have these pieces collapse starting at one end of the squab and working their way back. And again, spread falloff is a really good example for this. This guy is oblong enough that I could probably get away with a shape fall off, but the spread means that I don't have to worry about pieces falling off before the piece in front of them falls off. It'll look a little bit more natural here. And then again, I'm going to build some kind of control that I can use to direct where the spread starts. The sphere is perfectly good for that. So that's sort of right in the middle of where all those tentacles sit. Next, I need to check the fall off. And for that, again, I'm going to enable preview fall off and then display this as sprites because these are packed fragments and not regular packed primitives. So I need to change my start points mode to point cloud. My distance threshold is about right. So I'm going to go to my Animate tab and take the search radius down a bit. Now let's check to see how it spreads. So it's starting at this end on the tentacles and then working its way up the body. That's about where I want it. Let's add a little bit of noise as well. I'm going to go back and have the spread midway through so I can see the noise a little bit more clearly. I think I want this to be a bit noisier so I have some chunks kind of falling off a little bit more out of order, not too much. Let's bump the frequency up just a bit. Yeah, that looks about right. What I'm going to do with this fall off attribute now is I'm going to make it so that when the fall off reaches a certain threshold, the pieces are going to become active. In packed RBDs, you have an integer style attribute called active that if it's set to 0, a piece will act like a passive rigid body. It won't move at all. But if you set the active value to 1, the rigid body becomes active, and you can update that in the middle of a simulation if you have your rigid bodies properly configured. This means that as this fall off spreads across, the pieces will activate and they'll drop to the ground. The way I'm going to do this is with an attribute expression SOP. The attribute I'm setting is going to be custom, and it's going to be active. The active attribute is an integer. This is really important. You can't cast it from a float. It has to be an integer attribute in order for Bullet to understand it. And the expression is going to be MOPs falloff is greater than 0.9. So if I go to the spreadsheet, you can see that I have an active attribute now on these points, and it's set to 1 on a handful of them. And then as the spread increases, they all eventually become 1. Now I'll need to keyframe this spread value, so I'm going to start it at 0, set a key, and then at about frame, let's say 96, I'm going to set this to, let's see how high I need to make it. Let's do 1.2 to be safe. Okay, now let's send this into DOPS. I have an RBD packed object. It's going to be loading objects from the first context geometry. Now this is important because I'm changing active in SOPs, I'm changing that attribute, I need to enable overwrite attributes. And active is one of the default ones it accepts. This means that as the active attribute changes on the original points in SOPs, it's going to be reflected in DOPS. If you don't enable this, nothing will happen. Now I'm going to drop down a rigid body solver. This defaults to Bullet, so all I have to do is wire these in and it's good to go. I'm going to add a gravity force. And now I should have a ground plane for these to collide with. I'm going to lower it a hair. I know it's normally you want the ground plane at 0, but I already set this up, so we're just going to roll with it. I'm going to merge the ground plane in with the existing stream, connect it to the output, and now if I rewind, oh, I need to get rid of my fall off preview. Okay, so now I have my objects ready to go. And if I run the simulation now, as the pieces become activated, they drop to the ground. And that's just driven by a single fall off attribute. Okay, so back in SOPs, I've cached this whole simulation out. And now I can just play it back really quick. And there's a few things about this that I don't like. I've got this big chunk right here that's rocking back and forth all over the place. And that just looks a little weird to me. And I've got this little piece out here that's just going absolutely hog wild. And I want to stop him before he gets to that part. So I'm going to use a couple of MOPS nodes to fix that. First, I'll do this big piece. I'm going to select it and then hit delete to blast it. And then set this to delete non-selected, so I've just isolated this chunk. Next, I'm going to find the time that I want to lock him to. Let's say 105 is a decent rest position. So I'm going to time shift this piece to 105. And then I'm going to run MOPs extract attributes. Extract attributes will take the primitive intrinsics that define a packed primitive's transforms and convert those into template point attributes that you would use for instancing. MOPs apply attributes also reads those same template point attributes when setting goal transforms for things. So I'm going to extract the transforms from this piece and then apply it back to the original cache and use fall off to blend between the two. So let's make an apply attributes. I'm going to set the group on apply attributes to be the same as this primitive number, so I'm just affecting that single one, so 326. I'm going to set my rotate mode to set and the scale mode to replace, and that means that the transforms from this extraction operation are going to completely overwrite the ones in the main simulation. And then I'm going to connect the two together. So if I disable fall off, you can see that that thing is completely frozen in place. So now what I need to do is actually set a fall off attribute. To do that, I'm going to use MOPs plane fall off. I'm going to target that same piece, 326, and I'm going to start blending it, let's say right here, and finish maybe 110 frames later. Now when I play this back, that piece animates into the right position, it blends, and then stops where I wanted it to stop. This takes a little bit of finesse to get right sometimes, but a lot of the time it's better than simulating all over again. Now let's get that other piece. I'm going to go back to my original file cache, select the same primitive, and delete again. I'm going to rewire this so I'm not messing up my point order. Delete non-selected. So now I just have this piece. I'm going to find a frame that I want to be the goal transform. It's laying flat right here. That looks good enough. So we'll time shift him to 148. And then I can just merge these streams together, run the extract operation all at once. Now I just have to add this other primitive, 350, to the same mask for apply attributes. And again, I'm going to have to make another plane fall off because the timing isn't exactly the same between these two. I'm going to apply to 350, and now let's figure out the timing to blend this. Let's say we'll start somewhere around here, and then finish around here at 147. Now you can see that little piece that was going nuts before blends into that resting place, and it looks fairly reasonable. Now, there's obviously a lot more chunks wiggling around that I would want to fix, and maybe for this particular simulation, I might just want to have better practices in RBD to reduce all that jittering. But if you have a really, really difficult RBD simulation and just a few annoying pieces that are wiggling around, this is an easy way to just get those transforms to do what you want without having to resimulate. Now let's say I want to do one of those Instagram-worthy animations where this thing puts itself back together again. I can do that pretty easily with just another apply attributes to set a new goal transform. I'm going to do this with a spread fall off. Now I want to do this spread in sort of a fixed orientation, so I'm going to go back to my original geometry before the simulation and connect that as my input geometry. And then I'm going to make another sphere as my initial target. I want it to start from the center and then work its way outwards. So we'll go forwards a little bit here towards the end of the simulation. I'm going to preview fall off, display as sprites, scale the sprites down, change this to be a point cloud so it's reading my sphere as the input point. I'm going to turn my distance threshold down just a bit. And then let's go to the Animate tab and check our spread. We may need to increase the distance threshold just a little bit more. There we go. I just want to get that first blob to show up. Now I can go back here, check the spread. That looks good. Turn this back down just a hair. And then let's dress it up a bit with some noise. Let's check the spread again. That looks pretty good. It's coming out from the center, but not too evenly. Now what I'm going to do is copy this fall off from the static position back to the animated geometry. So the animated geometry goes in the first input. The spread fall off results go in the second. I'm going to copy MOPs fall off. Now I can do one last apply attributes. I can use the results of my simulation as the first input and the original geometry as the second. I'm going to set my rotate mode to set and my scale mode to replace so that the transforms are just simply blending. It looks like it's working, so all I need to do now is animate my spread. This looks like about the end of most of the interesting motion. So I'm going to set a key here. And a key here. And while we're at it, let's turn off these sprites. So now I've got an RBD destruction that I was able to do some tweaks to without having to resimulate. And I can get these pieces to lift up and form the top center first so that I don't get them colliding on top of each other too much, and blend back into the original position. So you can throw this straight on Instagram and everyone will love you. Let's talk very quickly about what's next for MOPs. As some of you might be aware, I've been developing some new MOPs tools over the past several months that I haven't yet released to the public. There's a lot of work left to do on them on top of updating the existing open source tools, so I don't have a definitive release date yet, but I wanted to take the opportunity to officially announce MOPs Plus and briefly show you some of the new toys. MOPs Plus is going to be a paid add-on for MOPs that adds new tools for both motion graphics and visual effects in the same spirit as the original nodes. There's going to be some new SOP tools, but the biggest upgrade here is the integration of MOPs into DOPs. This means that you can use MOPs-like interfaces to control physical forces natively inside Houdini. The new MOPs Apply Attributes DOP operates in much the same way as Apply Attributes in SOPs, in that it sets a goal transform for points or packed primitives, but also allows you to apply that goal using regular forces, wind forces, or by directly updating transforms. This Apply Attributes DOP, just like regular MOPs, is used as a framework that other DOP forces can be built on, including a straightforward transform DOP, as well as more complex forces like noise fields or moving along splines or meshes. All of these forces respond to fall-off attributes, and there are fall-off DOPs now too. The MOPs Typography SOP is a new SOP that aims to make working with type a little bit easier in Houdini. It has built-in controls for managing outline quality, extrusion, bevel quality, and it can output attributes in order to separate lines, words, or individual letters for easy grouping later. It also supports word wrapping within a bounding box. It even has a kerning handle so you can make kerning adjustments to individual letter forms. The resulting packed primitives are automatically aligned to the baseline for easy transformation. Here's an example of the new MOPs DOPs nodes. I'm using a combination of MOPs Apply Attributes, MOPs Object Falloff, and MOPs Transform in DOPs to scale these pigheads based on a moving falloff object in SOPs. This very simple example shows how intuitive MOPs DOPs can be. I'm just randomizing the transforms of these cubes and then connecting them to the input 2 of this DOP network. The MOPs Apply Attributes DOP can use the transforms of those randomized primitives as goal transforms for the original cubes, and it computes the forces necessary to reach those goals. It's a very straightforward way of guiding pops, RBDs, or even vellum geometry to a target. To wrap this all up, I wanted to point out where you can look for help with MOPs. The MOPs wiki on GitHub is the first place you should look for tutorials, installation help, and an overview of what all the different nodes do, complete with GIFs. The MOPs tutorial series on the wiki is the perfect place to start learning about how the whole system works, and it includes example files that you can download and play with, along with more GIFs. I'm constantly adding to it, and the full tutorial series should be completed in the next couple of months. Every node in MOPs also has a help card for information on every individual control and parameter. If you need help beyond what's available there, you can sign up for the MOPs forums, or you can try the MOPs users group on Facebook. And finally, you can just reach out to me directly if you can't post your scene publicly. And that wraps up this presentation. Thanks for watching, and please reach out if you have any questions at all.